This is lecture 17 for Data Science 100 and Data Science 200. The topic is gradient descent. So we're going to start by looking at something that's like gradient descent in one dimension. So let's say we have a function that we want to minimize, like a loss function. So here's an arbitrary function, our loss function, and it's f of x equals x to the fourth power minus 15x cubed plus 80x squared minus 180x plus 144. Now, there are many different approaches that we could use to minimize this function, and we're going to discuss one approach today that's called gradient descent. So here's a plot of that function that I just gave you, and you can see that looks like there's a minima, a local minima to the left, there's a local maxima in the middle, and to the right is our global minimum. Okay, so the intuition behind gradient descent in one dimension is that when we're to the left of a minimum, the derivative of that function will be negative. That is, it's going down. To the right of a minimum, the derivative is positive. That is, it's going up. So the derivative is going to tell us where we need to go and how far we need to go. And so we're going to use that to help us try to invent gradient descent. Now, before I jump into that, I want to pull up a website that I think is really useful for looking and exploring functions. So here's the website, and here I've got our function, our arbitrary function plotted in blue, and then I've got our derivative or a tangent line plotted in red. And we can see if we're over here to the left that our tangent, our derivative, is going to be negative. The function is going down. Then as we approach this local minima, it is still negative. And then when we reach that minimum, it goes to 0. And then when we move to the right of the minimum, it's now positive. It's going up. As we hit a local maxima, it goes back to 0. Then again, as we're to the left of our global minima, it's negative. It's going down. We hit our global minimum and it goes to 0. And then as we go to the right of our global minimum, again, it goes positive. It's going back up. All right. So you can explore the function using this graphing calculator. Okay. So I have a notebook here. You can also follow along with me that has the arbitrary function that we just defined. All right. And again, it's x to the fourth power minus 15x cubed plus 80x squared minus 180x plus 144. Okay, so here I've plotted it, and we can see if we look at it that, well, it looks like our minimum is going to be somewhere around here, like around 5.3. So our goal is going to be to figure out the exact minimum and to do that algorithmically. Now, instead of doing it algorithmically, we could just start by plugging in values to our function. So let's start with, let's say, 4.9. Okay, so that's a value of negative 0.5454. All right, so let's try a little bit to the right. We'll try 5.1. Okay, so we went down. So we're now at negative 0.644. And so let's go a little bit further to the right. All right, we're now at negative 0.69, so we're still getting smaller, so that's good. Let's go a little bit further to the right. Okay, so we went from negative 0.69 to now negative 0.68. So we went from going down to now we're going back up. So we could try this approach on a function, and it would be a very painful thing to do because we'd have to try lots of values, and it could take us a very long time to find the minimum. So a better approach might be to try brute force. So instead of me sitting here typing, or you sitting there typing these values, why don't we just simply generate an array of values and look for the value that is the minimum. Okay, so here I've got a simple minimize function, and I'm going to try that. I'm going to give it x from 1 to 7, and we're going to look at 20 different points. Okay? And then we're going to look for the minimum of our function. And it returns 5.42. Well, we already know from our manual exploration that that's actually not the minimum, right? That's to the right of the true minimum. So basically all I've done is just automate what I just did, which was to try and just look at a bunch of different points. And there's a number of issues here. It'll be a little bit helpful if I maybe instead graph this so we can actually see. So here we can see our points across the graph where we've sampled, taken a look at that plot to try and find the minimum. And what we can see is that we don't really have a point that's actually at the minimum. This is probably that 5.42 value that we had that's just to the right of our minimum. And so there's a couple of problems. First, this approach is really inefficient, and it has two major flaws. The first flaw is that if we don't get the range correct, if we, instead of 1 to 7, if I had done, something like 1 to 3.5, I would have found the minimum over here. And I would not have found the true global minimum. And so the result would be completely wrong. Even if we're within the correct range, our guesses might be too coarse. So, instead of 20, maybe I'd have to do 200, right? And that would make it even more inefficient. So, two problems here. You have to have the range correct, and you have to have the granularity correct in order to get an answer. So instead of just trying to pick all of our guesses in advance and not using the data itself to inform the guesses that we're making, we're just going to make one guess. And then we're going to let the data tell us which direction to go, right? And so we're going to iteratively improve on our choice of our guess. And so the key insight again here is that if the derivative of the function is negative, it means the function is decreasing. So we need to move to the right, that is, pick a higher value of x. On the other hand, if the derivative of the function is positive, then that tells us that the function is increasing, and so we need to pick values of x that are smaller or to the left. Okay, so the derivative is going to tell us which way we need to go. So, first thing we need is to take the derivative of our arbitrary function. And what I'm going to do is plot that. So it's a little bit of an awkward plot, but basically what we have here is we have our original arbitrary function. In blue, we have our derivative function, 4 times x cubed minus 45 times x squared plus 160 times x minus 180 is this line here, the dashed line in green. Okay, and we can see that to the left of a minimum, it is a local minimum, it's negative. To the right of a local minimum, it is positive. As we approach a local maximum, again, it goes back to 0. And then as we approach our global minimum, to the left, it is negative. We hit the minimum, it's 0. And when we go to the right of the minimum, it goes positive again. Now, to help you actually see the points that are actually interesting here, there's 3 of them. I'm plotting a line at 0. And so we can see here, this is our local minimum when our derivative goes negative. Again, here where we intersect is where we're at a local maximum, and our global minimum is going to be here where our derivative intersects 0. Okay, so now we can have some functions to help us plot things. And we can now again kind of look at those tangents from before. And here we can see if we pick the value 2, we can see our derivative is negative, so we know we need to move to the right. If we pick instead x of 6, we can see here our derivative is increasing, so we know we need to move to the left. So again, the derivative is going to tell us which direction we need to move, and that's what we're going to use to optimize the process of finding our minimum. Okay, so if we look at the derivative, let's say we start at 4. Okay, well, what's the derivative there? The derivative there is negative 0.4. So that's telling us it's negative, so we are to the left of where our minimum is. And so we need to move to the right, and we'll move just the value of that derivative. So we'll move to 4.4. Okay, so at 4.4, so that's moving us from here to somewhere about here. We see now the derivative is negative 0.6464. All right, so what this is telling us is you can see the slope here is greater, and we need to move over even more. All right, so we'll move over to what's effectively just over 5. And when we're at 5, we can see that our derivative now is negative 0.45. So at 5, we can see the slope is a little bit lower. We're going to continue moving over. And we're now starting to get closer to our minimum, right? Because we can see that it's dropped even more. Actually, I apologize. We can see that we've gone too far, actually, because now it's positive. It's 0.4166. So now that tells us we're on the other side of our minimum. So we need to go back to the left. All right. So we can see here how the derivative is telling us which direction we need to move, and we're just taking the value of the derivative as the amount that we're going to move. Okay, so that may have been a little bit confusing to see. Let's actually plot this, and it'll become a lot clearer. So we're going to start with a value of 4, and our next step, based on our derivative, is our derivative is going to be negative 0.4. So that's going to tell us we need to move to the right by 0.4. So we'll do that. We end up at 5.04 as the next value that we need to do. So we're going to go 5.04. Okay. And now you can see that we've kind of gone too far, right? But let's see what it tells us. Yeah, it tells us we've gone too far. So now it's going to move us to the left to 5.09. And now this moves us to the right again to 5.48. Okay, so we're going to go back to 5.48. And now this is moving us back to the left to 5.11. What's happening here? You can see we're oscillating. We're now back at 5.48. Weren't we just here at 5.48? We were. Okay, and now we're back at 5.1. So we're just oscillating back and forth. We're not actually finding the minimum. And the problem here is we're taking too large steps. Our steps are causing us to overshoot where we need to be for finding the minimum. So instead, what we're going to do is we're going to scale our jump. So rather than trying to jump the full value of the derivative, we're going to scale it by 0.3. All right. So now let's see what happens if we start at 4. Okay, so now we're going to take a smaller step. All right, so 4.12 rather. Next. All right, so our next step then will be 4.27. And then our next step after that will be 4.44. So you can see we're inching to the right, following the gradient down, but we're not taking giant steps, so we're avoiding overshooting. So our next value is going to be 4.63. All right, we're getting closer. 4.83 next. And now 5.01. And we're going to notice something here now. We're taking smaller steps even. right? Because our derivative here is going to be much smaller. And so now we're at 5.15. And then small steps, 5.24. And even smaller steps, now 5.29. And we're now at 5.31. And then we go to 5.32. And it looks like we've converged. So our minimum is somewhere around 5.32. So this is basically a recurrence, and we can write this as a recurrence relation. And the process we've described above is that our next value is going to be equal to our current value minus 0.3 times the derivative of our function that we're trying to minimize. This is the algorithm known as gradient descent. Okay, and so our next guess is going to be based on the sign and the magnitude of the derivative. Now, where did I pick 0.3 from? It was actually, I just picked 0.3. It's kind of arbitrary. And what we can do instead is parameterize our function. And typically that's represented by alpha, and alpha reflects what we call the learning rate. And so it's how fast our algorithm is going to try and find that minimum. Set alpha too large, and we may ping pong all over the place. Set alpha too small, and it'll take us a long time to converge. Okay, so we can write this up, and you can see we're going to have we have our derivative function, we have our initial guess, we have our alpha value, and we have the number of iterations that we want to try. So let's start. Here we'll start with an initial value of 4. We'll try an alpha of 0.4, and we'll go for 20 iterations. As you can see, we converge pretty quickly. All right. Well, what would happen if instead we use 0.3? We still converge relatively quickly. It takes us a little bit longer to converge. What if we used a value like 0.8? Well, it looks like actually we're converging much faster, right? We reach 5.32 in just a couple of steps. So, well, maybe we want to try something even larger. Oh, well, now that doesn't quite work, right? We never actually here in 20 iterations approach even, 5.32. The closest we might get is to 5.36. And this really reflects some of the challenges that we face with these numerical methods. You take a numerical methods class and you'll learn a lot more about the stability of these types of explorations and how you do good parameter selection. So here we can actually visualize what is happening here. And we'll start with, let's say we start at 4 and use 1.5. So here we can see we very quickly are narrowing in on what we were looking for, but we don't actually hit it. We just kind of ping pong back and forth and don't actually reach the value we were looking for. We could look at 0.3, and it's a little hard to see here, but it actually basically follows the curve. Instead, we could look at 0.7, and we'll see something similar. It basically follows the curve in finding it pretty quickly. Now, what about our initial guess? What if we started at, say, 1 instead? Well, here we can see actually we find it very quickly. What if we were to try a value like 0.4? Oh. So this is one of the challenges that we can have. And we'll come back to this in a moment. But here what we've ended up doing is we've ended up finding the wrong minima. We found a local minima and not our global minima instead. What if we picked 0.5? Well, so here, right, just a small set of changes, right? If we pick a different initial starting point, we pick a different learning rate, we can get very different answers from our algorithm. And in both cases, with starting at 1 and using an alpha of 0.4, we converged on a value. And similarly, using a starting value of 1, but a learning rate of 0.5, we converged on the true value. So we have to be careful when we're using these methods. So let's look at 1.2. So that didn't converge, ended up jumping all over the place and broke things. So that's another challenge we face. Let's try a little bit smaller value. And here we can see we take big jumps all over the place, but we actually do find pretty close to our minimum. So the challenge here is, we're just running our algorithm a simple fixed number of times. We're picking, our alpha and initial starting values pretty arbitrarily. And that's going to give us potentially arbitrary results. Now, more sophisticated implementations, they stop based on a number of different stopping criteria, like the error is getting too small or the error is getting too large. These are beyond the level of this class. Again, if you take a numerical methods class, you'll learn a lot more about how those sophisticated implementations work and how you actually do the parameter and initial point selection. So let's go back to our slides. And again, the intuition here behind one-dimensional gradient descent, to the left of the minimum, the derivative is negative. That guides us to move to the right. To the right of the minimum, the derivative is positive. That guides us to move to the left. The derivative tells us where to go and how far to go. So we've now put together the gradient descent algorithm. Alpha is our learning rate. If you make it too large, the algorithm won't converge. If you make it too small, the algorithm can take a very long time to converge. Now, gradient descent only finds a local minima. If the loss function has multiple local minima, then gradient descent is not guaranteed to find a global minimum. Now, let's suppose we have the following loss curve, this quartic loss curve. You can see that we have multiple local minima. Now, let's say we start with that initial green point as our initial starting point, right? And so let's look at how gradient descent might run on that. So we might select our next point to be on the other side of this local minimum, depending on our learning rate, and then select our next point will be pretty close. And then similarly, our next point, ends up finding this local minimum. And so we converge on a local minima of negative 15 when the true global minimum is 18. And this is because of a lack of convexity. For a convex function f, any local minimum that we have will also be a global minimum. So if our loss function is convex, then gradient descent will always find the globally optimal minimum point. All right, and here's the formal definition of a function being convex, but let's look at it intuitively. So if I draw a line between any 2 points on the curve, all values on the curve need to be either on that line or below that line. Right? And so here, the mean square error loss is a convex function. And so we can draw a line between any 2 points, and all of our values will be on that line or below that line. Here's a loss function, the one that we looked at earlier, the quartic loss, that is not convex. And you can see here we have some points that are below and some points that are above that line.